Hello, everyone. My name is Maxime Chevalier-Boisvert. I joined Shopify in 2020, and I've been working as a tech lead of the YJIT project since. YJIT is a project that was started in 2020 to build a new JIT compiler inside of CRuby to make Ruby seamlessly faster, that is, to maintain 100% compatibility. It was built at Shopify, but fully open source with some significant contributions from GitHub. And we try to take a data-driven approach to optimization, so have a broad, diverse set of benchmarks, benchmark often, and gather detailed metrics. YJIT is a team effort. I'm lucky enough to work with some of the best engineers in the world, and we've had many contributors to the project over the years. So in this talk, I'd like to go over some quick YJIT news updates. I'll talk a little bit about the history of supersonic flight, the traditional way of making Ruby code faster, why we might need a new approach, and I'll also talk about ProtoBuff, which is our pure Ruby implementation of ProtoBuff. So in YJIT news, Ruby 3.3 includes the third release of YJIT. YJIT was first in Ruby as part of Ruby 3.1, with some marked performance improvements in 3.2 and 3.3. Our main goal with 3.3 was to have something that was better tuned for production deployments out of the box. So with previous versions, often we had complaints that for some people, YJIT was not making their code faster and they had to adjust various command line parameters. So with YJIT 3.3, we tried to use less memory and to ship with better defaults. We also had a big push at the end of the year to fix as many bugs as possible. And I think this release has been very successful because we did not hear much after the release. We had no complaints, so usually that's a good thing. And we did end up getting some positive feedback about speedups in the wild. YJIT has been enabled on Ruby gems with speedups of up to 20%. It's also been enabled on Mastodon.social with some great performance gains. And there's been another big deployment, which you may or may not have heard about. Earlier this year, GitHub quietly deployed YJIT 3.3. The deployment went very smoothly, and they reported approximately 15% performance improvement. So if you visited github.com today, possibly you've used YJIT. We also had a shout out from DHH, the co-founder of Rails, who has been fully behind the work that we do. And with that, YJIT is going to be enabled by default in future versions of Rails. We've also had a shout out from the CEO of Shopify, reporting that ismyhostfastyet.com reports Shopify as the fastest hosting provider, and with YJIT providing something like a 20% speed up in response time, it's probably a significant contributor to this. So let me start by talking about the history of supersonic flight. So 1903 saw the first successful powered flights by the Wright brothers, with the Wright Flyer flying at approximately 48 kilometers an hour. But just over 10 years later, in Great Britain, the SE4 had a top speed of 217 kilometers per hour. So it was a very rapid progression in the speed of airplanes. At the beginning of World War II, Great Britain had the P-51 Mustang with a top speed of 690 kilometers per hour. And during World War II, there was a high competitive pressure to build faster and faster airplanes because faster fighter airplanes are better at dogfights and faster bombers are better at dodging fighters. So by the end of World War II, we also saw the deployment of the first jet-powered fighters on both sides, both from Germany and from the UK. So with World War II, there's lots of competitive pressure to build faster aircraft, but propellers tend to lose efficiency as they approach the speed of sound, which kind of puts an upper limit on how fast you can make propeller-driven aircraft. However, jet engines remove that limitation, and near the end of World War II, fighter pilots would encounter sometimes strange incidents when they accidentally broke the speed of sound while diving. Unfortunately, airflow behaves differently at supersonic speeds, so aircraft that are not designed to go supersonic tend to shake violently as they approach the so-called transonic region, and sometimes control surfaces can become reversed, so that makes it very easy for pilots to lose control in aircraft that are not specifically designed for this. We also have that drag rises sharply as we approach the speed of sound. And so we need several times more thrust to push through the transonic region and go supersonic. So in order to build supersonic aircraft, we need to rethink aircraft design. We need to design the aircraft in consequence. We need several times greater thrust to pass through the transonic region, but we also need to design aircraft with smaller swept back wings to reduce aerodynamic drag, and we need to deal with problems such as heating due to air compression. The first aircraft to go supersonic in level flight was the Bell X-1 rocket-propelled experimental aircraft in 1947. This aircraft was piloted by Chuck Yeager. And because this aircraft was rocket-powered, it could not fly for a very long time, so it needed to be airlifted by a modified B-29 Superfortress. Chuck Yeager made it to the rank of general and lived to be 97 years old. When looking at modern passenger aircraft, such as the 787 Dreamliner, there's been lots of incremental improvements made over the year to subsonic aircraft, but we can see that the airframe looks superficially at least very similar to, for example, Douglas DC-9 that first flew in 1965. But to build supersonic aircraft, you're working with a different set of constraints, and so you need a radically different design. But only 17 years after the first supersonic flights, in supersonic level flights, we already had built the SR-71 Blackbird, which go 3 times the speed of sound. So at this point, you might be thinking, this is RubyKaigi. When are you actually going to talk about Ruby? And I will. But first, let me talk about Python. So there are 2 main assumptions about performance with Python. The first is that Python is a slow interpreted language, and the second is that C is a fast compiled language. And so in the Python world, you're never allowed to complain about Python being too slow. If you say that Python is too slow, people tell you, well, just rewrite the slow parts of your program in C, because Python is for expressiveness, and if you want speed, you can use C or C++ or Go or some systems language. Unfortunately, I think this is not a good trade-off. And also, Ruby has kind of the same problem, which is leading to a sort of catch-22 situation, because the more code we write in C, the more code we can't optimize. And so it might be time to start thinking about how we can operate in a new regime. Widget is the engine pushing Ruby closer to the speed of C, and as Ruby gets faster, the cost of calling to C functions and translating data back and forth between C and Ruby becomes more and more expensive. So there's kind of an increase in drag. And we have this situation where Widget can't really optimize C code because it's kind of like a black box to us. And so this code is starting to get in our way. But I think as Ruby code gets faster, the complexity of maintaining C extension becomes less and less appealing. And so we're approaching a limit when it comes to optimizing Ruby performance. With Widget, we can make Ruby code run faster, but we can't optimize C. And calls between C and Ruby are relatively slow compared to the speed of machine code generated by Widget. And so how can we reach Ruby's maximum performance potential? Would it be possible, for example, to write more gems in pure Ruby code? And if we want to do that, do we have the tools in Ruby to do all of the things that C does as effectively in Ruby? So the first thing to look at, I think, if we take a step back, is why do people write C extensions? I think there's kind of 3 main reasons. One would be if you want to interface with some external I/O API that's not available in Ruby, or if you want to interface with system calls, for example, for outputting sound or graphical user interface or 3D graphics, for example, you might have no choice but to rely on C code. A second use case might be to improve performance bottlenecks. If you want to do some number crunching or matrix multiplication, for example, you're probably not going to be able to do that in Ruby, at least not with good performance. And the third use case, which is the one that I want to talk about, is to interface with a specific native library. In particular, at Shopify, because we're working in a web space, we interface with a lot of libraries that are just used for parsing and serialization. So let's talk about writing pure Ruby gems. The Redis client gem has two drivers. One is High Redis, which is the native C library binding, and it also has a pure Ruby implementation. My colleagues Aaron Patterson and Jean Boussier worked to improve the pure Ruby driver, and they found that with widget enabled, the new Ruby driver is about on par with the performance of the native C extension, in the same ballpark. And we think that the performance of this could be improved even further because the C API allows you to do things like pre-allocating hashes with the right size, but for now, this capability is missing in Ruby. So if we could add these capabilities to Ruby, then the pure Ruby driver could be even faster. There's also the GraphQL gem, which is used at Shopify and broadly across our industry. The default GraphQL parser relies on rack, which is fairly inefficient because there's a lot of Ruby to C and C to Ruby calls. But my colleague Aaron Patterson wrote a pure Ruby GraphQL parser, and with widget enabled, his parser could outperform the native C extension. There's a blog post on the Rails at Scale blog if you're interested in hearing more about this. And the third thing I want to talk about is ProtoBuff and ProtoBuff. So ProtoBuff is a binary serialization protocol created by Google. It's probably used at Shopify to serialize and deserialize various data. We're also adopting twerp as our internal RPC protocol, which is based on ProtoBuff. Unfortunately, Google's ProtoBuff is kind of an annoying dependency to manage. It's a common source of problems for Ruby upgrades. It's at the top of allocation profiles, and it's a common source of memory leaks and crashes. And so we wanted to look at whether it was possible to build a pure Ruby implementation that performs just as well as Google's native gem. And so we started working on ProtoBuff, which is our pure Ruby implementation of the Proto-tree spec. At this point, this is still experimental. It's kind of a proof of concept, but it has many attractive upsides. For example, it's very easy to debug and to maintain. It's easy for Rubyists to contribute because it's pure Ruby. It's highly portable. It will run anywhere that Ruby runs. There's no systems package dependency. It's also not tied to a specific Ruby ABI version. And it generates self-contained code with no runtime dependencies, which is also very appealing. This is an AI-generated image. Any resemblance to Shia LaBeouf is purely coincidental. So what does ProtoBuff do? Well, so like TinyGQL and Redis client, it deals with parsing and serialization. So with streams of bytes, it does some low-level bitwise operations to manipulate bytes. It allocates objects in memory. These are all things that are pretty easy to do in Ruby. And the way that it works is that it parses prototree.proto files, and it generates a self-contained piece of Ruby code to encode and decode ProtoBuff streams. We've also designed the code that we generate with widget in mind to leverage widgets for performance. So just how fast is it? Well, at first, when we benchmarked ProtoBuff against Google's library, we found that it was 7.43 times slower, which made us very sad. And at this point, we figured that we should probably just give up and go home. Just kidding. It turns out that Google's ProtoBuff parses streams lazily. So if you don't read any of the fields in the objects that you parse, it doesn't actually parse them. So when you benchmark decoding and reading the fields with Google's ProtoBuff versus our pure Ruby library, we're 2.36 times faster, which is cool. But there's more. If you enable widget, we're actually up to 90.45 times faster, a result which surprised even us. So there are some caveats that I should mention. Like I said, this is still experimental and a proof of concept. It's much faster than Google's library at decoding, but at the moment it is slower at encoding, just because we didn't spend any time optimizing the encoding logic. We're also thinking of using it internally at Shopify, but at this time it comes with zero support. It is open source, but if you use it, it's kind of like use it at your own risk. That being said, if you do use it and you find some issues with it, we will do our best to address the problems. So we built ProtoBuff in part just to see what it would take, how fast could we make it, what kinds of optimizations could we do in YJIT to make it run faster, and how hard would it be to make a faster pure Ruby ProtoBuff. And the answer is that it wasn't really all that difficult. So how did we do it? We kind of attacked the problem from two sides at once. One is we tried to generate Ruby code that we know YJIT will optimize well. And the second aspect is that we also added some optimizations to YJIT to make the Ruby code that we generate run faster. So is this cheating? Is it cheating to add optimizations to YJIT to make ProtoBuff run faster? Well, not really, because the optimizations that we added are things like faster core library methods for string getByte and string setByte. And these optimizations can benefit any code that uses these core methods. So with the optimizations we added to Ruby 3.4, we're able to run ProtoBuff about 14.5% faster. And these are some of the pull requests that we added that benefit ProtoBuff, but none of them are specific to the code that we wrote, really. This is some of the code that we generate to parse ProtoBuff. It's pretty convoluted. We wrote this code knowing full well, like, what are the specific strengths of weaknesses of YJIT. And so we wrote the code in a way that it's kind of like pre-chewed so that YJIT will run it as fast as possible. We don't recommend that you write your Ruby code this way, but we think since this is generated code, it's okay. So looking forward, there are still many areas of improvements, many pain points around doing low-level operations in Ruby. Ruby has lots of useful string methods, but these methods, to use them, you often need to allocate small strings, which is kind of a perf killer. Similarly, you have to do buffer reads into strings to do your parsing. So Ruby has IO buffer, which is oriented towards binary protocol, and has string IO. But none of these we found are really adequate for doing the kind of operations that we wanted. You also have the issue that encoding binary needs to be reset regularly when working with strings. This is a problem that we're working on hopefully solving for Ruby 3.4. And we're missing some APIs, for example, to allocate hashes and strings and arrays with a given capacity in Ruby. Those are problems that I think could probably be pretty easily addressed. But if we want to write more pure Ruby gems, we need to start thinking about kind of like what are the pain points and what are the things we could improve or add to Ruby to do those things more efficiently. So some takeaways. Traditionally, there's been a push to write performance critical code in C. With YJIT, this changes a bit. We're entering a new regime. And as Ruby code gets faster, I think the balance becomes different. So having to maintain C codes or native dependencies can be kind of a burden. It can expose you to some very breakable system dependencies. It can also make for code that is hard to debug, seg faults that are hard to trace. And in some cases now, we can make pure Ruby gems that are actually just as fast as C. And so to leverage YJIT, I think we need to cultivate our Ruby power, and we should try to make Ruby better for writing low-level code in the future. The YJIT team is working on YJIT 3.4. We're already seeing some nice performance improvements. We're working on improving the quality of the generated code. We're also working on quality of life improvements for analyzing performance in productions. And with Ruby 3.4, you should expect better performance across the board, comparable memory usage, and an even better tested and stable YJIT. And if you're feeling bold, of course, you can also try out Ruby Master and share your feedback with us. Of course, last thing I wanted to mention is that we're also hard at work at making optcarrots perform even faster with Ruby 3.4. So thank you for listening. And if you want to learn more about YJIT, you can follow our work on the Rails at Scale blog. You can check out the YJIT README. You can also reach me by email or on Twitter/X, and you can come talk to me after this talk. So thank you very much.